Yesterday, I randomly checked 10 fans who are students, asking them what a functional relationship is. Only one gave the correct answer. 9 couldn't explain it clearly. More than half of them didn't even know where the motion equations come from. They just memorized the formulas. If this describes you, then congratulations. In 5 minutes, you will fully grasp the essence of functional relationships and understand the underlying logic. No matter how the question types change, your physics scores will be firmly in your hands. Alright, in this lesson we're going to learn about functional relationships. Everyone has heard of the term functional relationship, but when it comes to explaining it clearly, many students don't really know how. So in this lesson, we're going to clarify it. What exactly is a functional relationship and what is its purpose? To study functional relationships, the first thing we need to understand is this first point. So, what is work? In our textbook, there's a formula for work, right? It's work equals force times displacement, or WRFXL. What does this represent? It means that work is the accumulation of a force over a distance in space. Multiplying force by displacement represents this accumulation in space. This is the work done by a force on an object, and we can also use this formula to calculate its magnitude. However, this formula only tells us a way to calculate it, but what is the physical meaning of work? Actually, when we talk about work, we need to understand it from the relationship between work and energy. In fact, work not only represents the accumulation of force over a distance, but it is also a measure of energy transformation. It serves as a standard for measuring energy conversion, or you could say it is an indicator of the amount of energy transformed. That is, the conversion between different forms of energy can be measured and indicated by work. Let me give you an example. Suppose we have a container, right? Inside this container, we place an object, and this object possesses a certain amount of energy. Of course, this energy can take various forms. It could be mechanical energy, gravitational potential energy, elastic potential energy, or kinetic energy. Depending on the given conditions in different problems, the type of energy may vary, but we refer to all of these collectively as energy. If an external force does work on the object, then its energy will change. We know that the formula distinguishes between positive work and negative work. So, what is positive work? It's equivalent to adding energy to our energy container, injecting energy into it. So, the energy of this object, the energy inside our container, will increase. Therefore, positive work will lead to an increase in energy. But if the force does negative work on the object, what happens? Of course, negative work will cause what? It will cause the energy value inside our container, inside our energy container, to decrease. We call this energy loss. So the relationship between work and energy is actually very simple. By doing positive work, the energy of an object increases. By doing negative work, the energy of an object decreases. The relationship between work and energy can be explained through this kind of example, which should make it very easy for everyone to understand. So the so-called work-energy relationship is actually the mutual transformation between work and energy, a process of mutual conversion. Next, let's take a look at some common forces and see how work and energy are converted between each other in these cases. In this lesson, let's go through them all at once. The 6 common types of work-energy relationships. The first is net force doing work. The second is gravitational force doing work. The third is elastic force. The fourth is when only gravity and elastic force are involved. The fifth is when forces other than gravity and elastic force do work. And the last one is a pair of mutually interacting sliding friction forces and their total work. After we sort out these 6 common work-energy relationships, you'll find that most problem types basically fall within the scope of these relationships. So, when you're solving problems, you'll be able to quickly and accurately find the right method and arrive at the correct answer. First, let's look at the first one, net force doing work. Let's consider what kind of energy change is caused when the net force does work on an object. According to the work-energy theorem, the work done by the net force on an object is equal to the change in its kinetic energy. So when the net force does work, it results in a change in the object's kinetic energy. The work done by the net force leads to this change. The change in kinetic energy. So what is our formula? It's the formula from the work-energy theorem. W equals delta K, which is K2 minus K1. This is the work-energy theorem that we've learnt. Therefore, in the future, whenever you encounter a problem where you're told the work done by the net force, or you can calculate the net force and the work it does from the given conditions, what can we use? The work-energy theorem, right? We use the formula from the work-energy theorem. So, let's organize our thoughts. When it comes to these common energy relationships, we can clearly understand that when we see a problem, based on the information given, how do we choose the appropriate energy relationship to solve it? How do we solve for the answer to the problem? The first point is that the work done by the net force results in a change in the kinetic energy of an object. The second point is about the work done by gravity. In fact, many students haven't fully grasped the concept of work done by gravity because they can't clearly distinguish the relationship between the work done by gravity and the change in gravitational potential energy. First of all, when we talk about the work done by gravity, what kind of energy change does it bring about? It is the change in the object's gravitational potential energy, right? A change in gravitational potential energy means that as long as gravity does work, the gravitational potential energy will inevitably change. It is a change in gravitational potential energy. Now, when we study the work done by gravity, there is a very important point. When gravity does positive work, When gravity does positive work, what happens to the object's gravitational potential energy? We call it EP, and its gravitational potential energy decreases. When gravity does positive work, its gravitational potential energy decreases. So what about when gravity does negative work? When gravity does negative work, its gravitational potential energy increases. Now, this relationship, many students have trouble remembering it because this conclusion is actually the opposite of our intuition. When gravity does positive work, its gravitational potential energy actually decreases. And when gravity does negative work, its gravitational potential energy actually increases. Actually, there's no need to memorize this. You can derive it yourself or use examples to understand it. For instance, let's say this is our horizontal ground and an object moves from point A, which is at a higher position, down to point B. It's moving downward, right? Look, from A to B, what kind of work is gravity doing? Its height is decreasing, so gravity is doing positive work, isn't it? But after it reaches point B, its height above the ground is lower, so its gravitational potential energy decreases, right? So for this kind of conclusion, there's no need to memorize it by rote. Just understand it conceptually. Therefore, we can see the relationship between the work done by gravity and energy transformation. This formula is that the work done by gravity equals what? It equals the negative value of the change in gravitational potential energy, right? Because when gravity does positive work, the gravitational potential energy decreases. When it does negative work, the gravitational potential energy increases. So there's a negative sign in front and it equals the negative value of the change in gravitational potential energy. So what does it also equal? It equals the gravitational potential energy in the initial state minus the gravitational potential energy in the final state. EP1 minus EP2. EP1 is the gravitational potential energy of the object in its initial state. EP2 is the gravitational potential energy in the final state. In this way, it can figure out the relationship between the work done by gravity and the change in gravitational potential energy. So if you come across a problem involving the work done by gravity, you need to understand how the work done by gravity and gravitational potential energy are converted between each other. At the same time, you should also know how to calculate the quantitative relationship between them. This is our second functional relationship involving the work done by gravity. The third one is the functional relationship for the work done by the elastic force of a spring. We know that both the elastic force of a spring and gravity are conservative forces, and the way they do work is actually the same. So we can draw an analogy to the functional relationship for the work done by gravity. Similarly, the work done by the elastic force of a spring will result in a change in the elastic potential energy of our system. Whenever the elastic force of a spring does work, it will definitely cause a change in the object's elastic potential energy. In the same way, just like with the work done by gravity, when the elastic force does positive work, the elastic potential energy of the object decreases, right? When the elastic force does negative work, the elastic potential energy of the object increases. You can also think about it like I do. As we just discussed, try to understand and memorize this conceptually. Give an example, understand it, and that's enough. Then, regarding the formula, the work done by the spring force is also equal to the negative value of the change in elastic potential energy. That is, it equals the negative of the elastic potential energy of the object's initial state. That is, subtract the elastic potential energy of the final state. For the spring force, we can draw an analogy to the work done by gravity. Then, the fourth point, in the case where only gravity and elastic force do work. When only gravity and elastic force are doing work, this is actually what we refer to as the conservation of mechanical energy, right? So when only gravity and elastic force are doing work, the energy affected is... The energy involved here is our mechanical energy. At this point, it is the conservation of mechanical energy, which is what we refer to as the conservation of mechanical energy. The formula is also very simple. The change in the object's mechanical energy, delta E, is equal to 0. Or in other words, the object's mechanical energy in the initial state is equal to its mechanical energy in the final state. Yes, this is the conservation of mechanical energy. This is very straightforward, so we won't go into further detail here. Okay, the fifth point is about the work done by forces other than gravity and elastic force. If we exclude gravity and elastic force, what should the work done by the other forces be equal to? At this point, the work done should be equal to the change in mechanical energy. That is, the work done by forces other than gravity and elastic force must cause a change in the object's mechanical energy. This means it leads to a change in the object's mechanical energy, and in this case, it no longer falls within the scope of mechanical energy conservation, right? Alright, so at this point, the work done by other forces is converted into the object's mechanical energy. The magnitude of the work is equal to the change in mechanical energy. The amount of work done equals the change in mechanical energy. Of course, if other forces do positive work on the object, its mechanical energy increases. If they do negative work, then the mechanical energy decreases. This is our fifth point. When forces other than gravity and elastic force do work, this is the relationship between work and the change in mechanical energy. And finally, the last point is a challenging aspect within our work-energy relationships, which is a pair of mutually interacting sliding friction forces. As for the total work done, the pair of mutually interacting sliding friction forces have a relatively more complex situation when it comes to work. In the future, Brother Song will make a separate video to explain this to everyone. Today, we'll just briefly go over what mutually interacting sliding friction forces are. Let me give you an example. For instance, we've talked before about a block model, right? On a horizontal surface, there is a wooden board, and on that board, there is a wooden block. Between the board and the block, if there is relative sliding, then there will be a pair of relative sliding friction forces between them. For example, if the block is moving to the right relative to the board, then the block will experience a friction force to the left, horizontally. What about the board? It will experience a friction force to the right, horizontally. These two friction forces together form a pair of interacting sliding friction forces. Both of these forces are doing work. However, the sum of the work they do, that is the total work done by this pair of interacting sliding friction forces, what is it? It is negative. They are definitely doing negative work. You can understand it this way. When there is relative motion between two objects, there will definitely be friction generating heat. There will definitely be heat produced by friction. In this case, it is definitely doing negative work. And the total work done by the friction force will definitely lead to what? An increase in the internal energy of the system. Moreover, it will definitely cause an increase in the internal energy of the system. That is to say, as long as there exists a pair of interacting kinetic friction forces, and you must remember, it has to be kinetic friction. If it is static friction, when there is no relative motion between the two objects, no relative sliding, then there is no heat generated by friction. It must be kinetic friction. In this case, there will definitely be heat generated by friction, leading to an increase in the system's internal energy. Because it is precisely the relative sliding between objects that causes frictional heating. So, what is the amount of heat Q? It equals the kinetic friction force multiplied by delta X, which refers to the relative sliding between the objects. For two objects sliding relative to each other, the heat generated by friction between them equals the kinetic friction force between them multiplied by delta X. Delta X is the relative displacement between the two objects, called relative displacement. So this is the energy transformation situation for a pair of interacting kinetic friction forces. What about this pair of friction forces? The work they do is always negative work, and it will cause the internal energy of the objects to increase, which means there will definitely be frictional heating. At this point, the amount of heat generated by friction is equal to the kinetic friction force multiplied by the relative displacement. As for the sixth point, the transformation between the work done by kinetic friction and energy, we will cover this in detail in a separate video later. It's relatively more complex, so we won't go into detail about it in this session. These are some of the common work-energy relationships, their transformations and calculation methods. Once you have learned them, you can apply them in your future problem solving